Alrighty, so excuse me, we have to finish the bottom. I have to keep my videos short or they don't upload well. So let's finish the bottom here. Here we have an object. And what is it doing? Is it moving away or getting closer? Well, it's moving away, and it's initially starting off kind of slow. You can see that the time is moving forward, but the distance is not increasing very quickly. But then all of a sudden, as you get to right about here, the function just takes off and the distance increases rapidly over a short amount of time. Okay, so the distance almost triples in half the time it took us to even get this far. So basically an objecting, what did I write there? An object is moving away at an increasing rate. Okay, at an increasing rate. I'm sorry about my handwriting with this. Whereas the next one, the object is moving away very quickly. It covers a very long distance in a very short amount of time. It's a little short amount of time with a far distance. And then it kind of levels off. So it's moving away. It's not getting closer, but it's moving it away at a decreasing rate. It's getting slower. Oops, moving, not mowing. It's moving away at a decreasing rate. Okay, so let's take a look at these scenarios and then let's look at the graphs here. So match each distance versus time graph with the correct description. So we've got Kaylee got on a bus at her house. The bus made 2 more stops before it arrived at school. Which of these graphs, looking at them, matches that description? All right, let's read scenario number 2. Brennan and his dad left for school in his dad's car. They got stopped at the train tracks for several minutes before they were able to continue to school. And the last scenario, Cameron left for school with his mom, but remembered he left his English project at home. She took him back home to get his project, and then they headed back to school without any stops. Remember, what does it look like when you stop? Your distance does not increase or decrease, but your time continues forward. So if you look at this first graph, this is obviously a stop right here. Somebody stopped for quite a while. In the second graph, in the second graph, there were 2 stops made. One here for a short amount of time and one here for a short amount of time. In the third graph, there's a little stop here and a little stop here, but then there are no stops in between. So now looking back over your scenarios, look at the first one. She got on the bus at her house. So remember I told you that time kind of represents this bottom x-axis. This represents where you are, where you start. So Kaylee got on the bus at her house. So she's starting here, and then she's moving away from her house. Her distance away from the house is increasing, but then it made 2 stops. Well, here we go. We have a stop here where we're waiting for people to get on. The distance doesn't change from her house. Then the bus continues on away from the house towards school. Then there's another stop, a second stop. More kids are getting on. And then that continued increase of distance away from the house till you get to school. So this would be the graph for A. Brennan and his dad left for school in his dad's car. They get stopped at the train tracks for several minutes before they were able to continue to school. So looking at the first graph and the third graph, we see that the third graph has us moving our distance away from the house, which remember is this bottom line, and then returning back to the house. Now remember, this isn't a map. To return to the house, we're not going back to the origin because time can't go backwards. I'll repeat that. Time cannot go backwards. So when you return to your house, time is still going forwards. You're just returning to this x-axis here. Even though you're returning not the exact same location on the grid, but because this isn't a map, the x, the whole bottom line represents your house. So your distance back to your house decreased as time continued to increase. Then, of course, why is there a stop then? Well, because Mom's sitting in the car while the car idles, and Brennan runs in, or no, it's Cameron, goes in to get the English project out of the house, and then comes back out and has to put it in the back of the trunk, and then they drive at a consistent rate all the way back to school. Again, distance away from the house increasing all the rest of the way to school. So this one is going to be the graph for C. Looking at A, the key here to A, or not A, B, sorry. The key to B is that they got stopped at the train tracks for several minutes. Remember, when we're in rest, we're stopped, whether we're sitting on a park bench or waiting for someone at a locker, the distance does not change from your origin spot. But time continues to move forward. Therefore, this straight flat line, this zero slope, represents a stop in distance. The activity is still going on because time's still ticking, but the distance from your original place isn't changing. So this line represents sitting at the train tracks, waiting for the train to go by, and then continuing on your way, increasing your distance away from your original starting point. So this would be the graph for B. So why don't you go ahead and take a look at number 2. This is one where you would have to draw the scenario. Pause the video and then restart the video when you're ready to check your answer. Okay, so assuming you paused it and you now have a graph that you can compare it to, Adam left his friend Brody's house and started walking home. So a walk is not going to be a straight line up or a real steep line, because that's going to be increasing your distance at a quick amount of time. A walk is a casual stroll. So we're going to do kind of a slant like this. Then he realized he left his phone at Brody's, so he turned around to get it. Again, we don't go back to the origin. He's going to walk probably the same amount of speed that he walked to get where he was the first time. And then he's coming back to Brody's. So this whole bottom line represents Brody's house. And the function that we're drawing represents moving away from Brody's house and moving back towards Brody's house as time continues to tick on. Adam left Brody's a second time and started to walk home. Probably still about the same amount of speed. Then Adam stopped halfway to talk to a friend that he passed. So he could stop right about, we'll say here. I doubt he stops at the exact same place where he forgot his phone. And when you're stopping to talk to a friend, whether you're standing or sitting, you've got a line of zero slope. So remember that time is marching on, but your distance from your origin isn't changing, your original spot. So his distance away from Brody's house is not changing as he is standing there talking to a friend. Then he quickly runs home to make it in time for dinner. This line needs to be steeper. And the reason for that, you don't want a straight line, but you want to cover a lot more distance in a quick amount of time. You only have this amount of time down here to cover this much distance. Because he's running, he's going to get there faster in less time. Okay, you try the rest on your own.